Hello everybody, welcome to Pencil College. So in the previous few videos, we have already covered on how to differentiate polynomials, different rules that we can learn. So now we are moving into the application of differentiation, okay, and what it can do for us. Okay, so the first chapter is chapter 15.1, which is the rate of changes. Okay, in this video, we will first learn how to use the first derivative to identify increasing and decreasing function, as well as a recap to understand that the gradient um, of a certain function is also known as the rate of change at that point. Okay, so firstly, we want to understand that, for example, let's say I take dy dx of a function, say fx. What I'm actually doing by doing dy dx is finding the gradient function. Okay, so the gradient function tells me a lot of things. So basically, if I get a gradient function and I sub in a certain x value into the gradient function, I find the gradient at that point. Okay, so this is just a recap of what we have just done. So for example, I have any arbitrary fx function. Let's say I want to find this point at x equals to a. Okay, I should label my axis first. Okay, so for example, I want to find the gradient at this point. Okay, so I just have to sub in to find, like, for example, f prime of a. Then I would get my gradient at a. Okay, so with this, we can actually use it to identify increasing and decreasing functions. So the rate of change is also understood as the gradient here. Okay, so this is what I mean by the second line. So let's try an example to make things clearer. For example, an nth position with respect to a point O can be given by s is equals to t squared plus 5, where s is its displacement and t is the time. So find the rate of change of displacement with respect to time. So when I say find the rate of change of displacement is s, with respect to time, time is t. What I mean is I want to find ds dt. So this is what I really want. Okay, so it's easy to find ds dt. So ds dt is just equals to differentiating s with respect to t would just give us 2t over here. Okay, I'm very sure you're very familiar with this. And then find the rate of change of displacement at t equals to 1. So for example, at t equals to 1, then ds dt is equals to 2 times 1, which is 2. Okay, so in actual case in physics, I can also write 2 meters per second if this is in SI units. Okay, so this is actually the velocity. This is actually the velocity v in physical sense. Okay, for those of you who take physics as well. So basically, when I say that I want to find the rate of change of displacement or rate of change of something with respect to another thing, what I mean is by taking the derivative. Okay, so how displacement change according to time. So s will be in the numerator and t will be in the denominator. Actually, this one should not be viewed as a fraction, but it can be viewed as rather the change in s over the change in t in the limit where t is very small. Okay, another thing that the gradient function can do for us is to find that the graph is ever increasing or ever decreasing. Okay, so how do we do that? So let's try this example and you understand. So show that the graph of y is equals to x cubed plus 6x squared plus 3x plus 4 is always increasing for x is more than 0. Okay, so let us do so we know that we have to do the derivative. So let us just try doing the derivative and see what we get. Okay, so the x cubed becomes 3x squared, 6x squared becomes 12x, and the 12x, and the 3x just becomes 3, 4 becomes 0. Okay, so this is my gradient function. Okay, well, so for x is more than 0, tell me what happens to the gradient function. Okay, so let's just see. If x is more than 0, this term would be more than 0, this term will be also more than 0, and this term definitely is more than 0. So if I add 3 terms that are more than 0, then my dy dx will always be more than 0. So what does it mean when my dy dx is more than 0? It means gradient always larger than 0. Right? So when my gradient is always larger than 0, there is no way for my graph to ever decrease, because my gradient must be more than 0. So for example, at a certain point, let's say I take the gradient is more than 0, right? So the graph has to be increasing. So at another point I take the gradient, it is the gradient is still positive gradient. It's still an increasing graph. So if it is a graph that keeps on increasing, then the gradient, or rather the whole graph, would definitely be more than 0. Okay, and it's always increasing. Okay. Okay, so in this case the graph is also always more than 0. Okay, for values of x more than 0, you can try subbing the value of 0 in, and you realize that the value at 0 is more than 0, and the graph is increasing, therefore it is more than 0. Okay, but we can also show from the gradient function that it's always increasing. Okay, so in summary, we have actually used the first derivative to identify increasing and decreasing function, and understanding that the gradient is also the rate of change at that point. Okay, so let me summarize that using symbols. Okay, so basically if I take dy dx and it's more than 0, then this is an increasing function. And if I take dy dx and this dy dx is less than 0, then this is always a decreasing function. And bear in mind that it has to be always larger or always smaller before I can call it an increasing or decreasing function. Okay, so also finding the rate of change. Rate of change is very easy. The rate of change um, uh, would mean the rate of change with respect to time if it's not specified. Okay, so if we specify like rate of change of y with respect to x, then that would be dy dx. If I just say the rate of change, then it would just mean that it is a rate of change with respect to time. Okay, so the other thing, we also know that rate of change can be found using for example dy dt or ds dt in our example. Okay, here are some practice questions you can try out on your own. The exercises are rather simple, so I believe you can manage them. Okay, thank you for watching this video. For more videos, please visit pencilcollege.com. Thank you.